is than its expected load, calculated as the ratio of its ultimate strength or yield strength to the actual working stress or wear, with higher FOS numbers, for example 2, 3, or more, indicating a greater safety, while an FOS of 1 means failure at the design load. And what are the key concepts? The definition. A measure of redundancy or margin against failure, showing how much over designed something is for normal use. The next one is formula. Factor of safety is equal to ultimate strength or load divided by working stress or load. The next concept is material dependence. For ductile material like steel, yield strength is used. For brittle materials like concrete, ultimate strength is used. The next one is importance. Accounting for uncertainty ensures reliability and prevents catastrophic failure in bridges, building, aircraft, and machinery. Example and interpretation. If the FOS is equal to 1, failure occurs exactly at the design load unacceptable for most applications. If FOS is equal to 2.25, a chair designed to hold 360 pounds is used by someone weighing 160 pounds, which means 360 divided by 160 is equal to 2.25, meaning it's 2.25 times stronger than needed for that person. The next concept is variant factors. Aerospace uses lower FOS weight critical, while pressure vessels and buildings use higher factors for more safety. Why it is used? The first reason is uncertainty. Material properties vary, load are unpredictable, manufacturing isn't perfect. The next reason is safety. Protect against misuse, environment change, and unexpected events. The next reason is design helps engineers choose appropriate materials and dimensions to meet safety codes and standards. For example, AISC and ASME. In engineering, a factor of safety FOS or safety factor SF expresses how much stronger a system is than it needs to be for its specified maximum load. Safety factors are often calculated using detailed analysis because comprehensive testing is impractical on many projects such as bridges and buildings. But the structure's ability to carry a load must be determined to a reasonable accuracy. Many systems are intentionally built much stronger than needed for normal usage to allow for emergency situations, unexpected loads, misuse, or degradation. For reliability. The next one is margin of safety. MOS or MS is related measure expressed as a relative change. The definition of margin of safety. There are two definitions for the factor of safety: the ratio of structures, absolute strength, structural capability to actual applied load. This is a measure of the reliability of particular design. This is a calculated value and is sometimes referred to for the sake of clarity as a realized factor of safety, constant required value imposed by law, standard, specification, contrast, or custom to which a structure must conform or exceed. This can be referred to as a design factor of safety, or required factor of safety. The realized factor of safety must be greater than the required design factor of safety. However, between various industries and engineering groups, usage is inconsistent and confusing. There are several definitions used. The cause of much confusion is that various reference books and standard agencies use the factor of safety definition and terms differently. Building codes, structural and mechanical engineering textbooks often refer to the factor of safety as a fraction of the total structure capability over what is needed. Those are realized factors of safety first use. Many ungraduated strength of materials books use factor of safety as a constant value intended as a minimum target for design. And about the calculation. There are several ways to compare the factor of safety for structures. All the different calculations fundamentally measure the same thing: how much extra load beyond what is intended a structure will actually take or be required to withstand. The difference between the methods is the way in which the values are calculated and compared. Safety factor values can be thought of as a standardized way for comparing strength and reliability between the systems. The use of factor of safety doesn't imply that an item, structure, or design is safe. Many quality assurance, engineering, design, manufacturing, installation, and end-use factors may influence whether or not something is safe in any particular situation. Design factor and safety factor. The difference between the safety factor and design safety factor is as follow. The safety factor or real stress is how much the design part actually will be able to withstand first usage from above. The design factor or working stress is what this item is required to be able to withstand second usage. The design factor is defined for an application generally provided in advance and often set by regularity building codes or policy and is not an actual calculation. The safety factor is a ratio of maximum strength to intended load for the actual item that was designed. By this definition, a structure with an FOS of exactly 1 will support only the design load and no more. Any additional load will cause the structure to fail. A structure with an FOS of 2 will fail at twice the design load. The chapter of margin of safety. Many government agencies and industries, such as aerospace, require the use of margin of safety (MOS or MS) to describe the ratio of the strength of the structure to the requirements. There are two separate definitions for the margin of safety, so care is needed to determine which is being used for a given application. One usage of margin of safety is as a measure of capability like FOS. The other usage of MS is as a measure of satisfying design requirements, which means requirement verification. Margin of safety can be conceptualized along with the reserve factor explained below to represent how much of the structure's total capability is held in reserve during loading. Margin of safety as a measure of structural capability. This definition of margin of safety, commonly seen in textbooks, describes with an additional load beyond the designed load, a part can be withstanded before failing. In effect, this is a measure of excess capability. If the margin is zero, the part will not take any additional load before it fails. If it is 1, it can withstand one additional load of equal force to the maximum load it was designed to support, for example, twice the design load. Margin of safety as a measure of requirement verification. Many agencies and organizations, such as NASA and AIAA, define the margin of safety including the design factor. In other words, the margin of safety is calculated after applying the design factor in the case of margin of zero. The part is exactly the required strength. The safety factor would equal the design factor. If there is a part with a required design factor of 3 and a margin of 1, the part would have a safety factor of 6, capable of supporting two loads equal to its design factor of 3, supporting 6 times the design load before failure. A margin of 0 would mean the part would pass with a safety factor of 3 if the margin is less than 0 in this definition. Although the part will not necessarily fail, the design requirement has not been met. A convenience of this usage is that for all applications, a margin of 0 or higher is passing. One doesn't need to know application details or compare against requirements. Just glancing at the margin calculation tells whether the design passes or not. This is helpful for oversight and reviewing on projects with various integrated components, as different components may have various design factors involved, and the margin calculation helps prevent confusion. For successful design, the realized safety factor must always equal or exceed the design safety factor so that the margin of safety is greater than or equal to 0. The margin of safety is sometimes but infrequently used as a percentage. For example, a 0.50 margin of safety is equivalent to 50% MS. When a design satisfies this test, it is said to have a positive margin, and conversely, a negative margin when it doesn't. In the field of nuclear safety, as implemented at US government owned facilities, the margin of safety has been defined as a quantity that may not be reduced without review by controlling government office. The US Department of Energy publishes DOEG implementation guide for use in addressing unreviewed safety question requirements as a guide for determining how to identify and determine whether a margin of safety will be reduced by a proposed change. The guide develops and applies the concept of quantitative margin of safety that may not be explicit or quantifiable, yet can be evaluated conceptually to determine whether an increase or decrease will occur with a proposed change. This approach becomes important when examined designs with large or undefined historical margins and those that depend on soft controls such as programmatic limits or requirements. The commercial U.S. nuclear industry utilized a similar concept in evaluating planned change until 2001, when 10 CFR 50.55 was revised to capture and apply the information available in facility-specific risk analysis and other quantitative risk management tools. Reserve factor. A measure of strength frequently used in Europe is the reserve factor, with the strength and applied loads expressed in the same units. The reserve factor is defined in one of two ways, depending on in the industry. Yield and ultimate calculations. For ductile material, for example, most metals, it is often required that the factor of safety be checked against both yield and ultimate strength. The yield calculation will determine the safety factor until the part starts to deform plastically. The ultimate calculation will determine the safety factor until a failure. In brittle materials, the yield and ultimate strength are often so close as to be indistinguishable, so it is usually acceptable to only calculate the ultimate safety factor. Choosing design factors. Appropriate design factors are based on several considerations such as the accuracy of predictions on the imposed loads, strength, re-estimates, and environmental effects to which the product will be exposed in service, the consequences of engineering failure, and the cost of overall engineering the components to achieve the factor of safety. For example, components whose failure could result in substantial financial loss, serious injury or death may use a safety factor of 4 or higher, often 10. Non-critical components generally might have a design factor of 2. Risk analysis, failure mode, and effects analysis and other tools are commonly used. Design factors for specific applications are often mandated by law, policy, or industry standards. Buildings commonly use a factor of safety of 2 for each structural member. The value for buildings is relatively low because the loads are well understood and most structures are redundant. Pressure vessels use 3.5 to 4, automobiles use 3, and aircraft and spacecraft use 1.2 to 4, depending on the application and materials. Ductile metallic materials tend to use the lower value while brittle materials use the higher values. The field of aerospace engineering uses generally lower design factors because the costs associated with structural weight are high. For example, an aircraft with an overall safety factor of 5 would probably be too heavy to get off the ground. This low design factor is why aerospace parts and materials are subject to very stringent quality control and strict preventative maintenance schedules to help ensure reliability. A usually applied safety factor is 1.5, but for pressurized fuselage is 2, and for main landing gear structures is often 1.25. In some cases, it is impractical or impossible for parts to meet the standard design factor, and the penalties, mass or otherwise, for meeting the requirements would prevent the system from being viable, such as in the case of aircraft or spacecraft. In these cases, it is sometimes determined to allow a component to meet a lower than normal safety factor, often referred to as waiving the requirement. Doing this often brings with it extra detailed analysis or quality control verifications to assure the part will perform as desired, as it will be loaded closer to its limits. For loading that is cyclical, repetitive, or fluctuating, it is important to consider the possibility of metal fatigue when choosing factor of safety. A cyclic load, well blue, a material's yield strength can cause failure if it is repeated through enough cycling. Engineering tolerance. Engineering tolerance is the permissible limit or limits of variation in the physical dimension, a measure value of or physical property of a material, manufactured object, system, or service. Other measured values such as the temperature, humidity, and etc. In engineering and safety, physical distance or space tolerance, as in a truck, lorry, train, or boat under a bridge, as well as a train in a tunnel. In mechanical engineering, the space between a bolt and a nut or a hole, and etc. Dimensions, properties, or conditions may have some variation without significantly affecting functioning of system, machines, structures, and etc. A variation beyond the tolerance, for example, a temperature that is too hot or too cold, is said to be non-compliant, rejected, or exceeding the tolerance. Considerations when setting tolerance. A primary concern it is determine how wide the tolerance may be without affecting other factors or the outcome of a process. This can be by the use of scientific principles, engineering knowledge, and professional experiments and experiences. Experimental investigation is very useful to investigate the effects of tolerance, design of experiments, formal engineering, evaluation, and etc. A good set of engineering tolerance in a specification by itself doesn't imply that compliance with those tolerances will be achieved. Actual production of any product or operation of any system involves some inherent variation of input and output. Measurement error and statistical uncertainty are also present in all measurements. With a normal distribution, the tails of measured values may extend well beyond plus and minus 3 standard deviations from the process average. Appreciable portions of one or both tails might extend beyond the specified tolerance. The process capability of systems, the materials, and products need to be compatible with the specified engineering tolerances. Process control must be in place, and effective qualities management systems such as total quality management needs to keep actual production within the desired tolerance. A process capability index is used to indicate the relationship between the tolerance and actual measured production. The choice of tolerance is also affected by the intended statistical sampling plan and its characterized such as the acceptable quality level. This relates to the question of whether tolerances must be extremely rigid, high confidence in 100% conformance, or whether some small percentage of being out of tolerance may sometimes be acceptable. A novel strange reduction method for a slope stability assessment based on a finite element method. Ensuring the stability of slopes is critical to safe operation of geotechnical engineering. Evaluating a slope stability to minimize geologic risks induced by this stabilization is significantly reducing casualties and property damage. A conventional single coefficient strange reduction method is widely applied in slope stability analysis, but this method ignores the attenuation degree of different parameters in the slope destabilization. A new double strange reduction method considering different contributions of mechanics parameters is proposed in this study, and simulation for evaluating the stability of non-homogeneous slope. First, the role of each mechanics parameters in the slope destabilization was investigated theoretically and numerically using COMSOL software simulation, and the result indicate that the effect of elasticity, Poisson ratio, and soil gravity on the evaluation of factor of safety or FOS are insignificant and can be neglected compared with the cohesive force and angle of internal friction. Next, an improved method was constructed to correlate the FOS with cohesive force and the angle of internal friction. Then, a numerical method was constructed based on the computation of the mathematical mechanical relationship between FOS and the mechanical parameters, and the stability of a slope is estimation based on the Moore Coulomb yield criterion. Finally, the double strange reduction coefficient method proposed in this simulation, the limit equilibrium method and the traditional finite element strength reduction coefficient method were applied to non-homogeneous slopes and slopes containing a soft underlying layer for comparison, and the difference between them was within the range of the positive negative 5%. The results indicate that both the limit equilibrium method and the traditional finite element strength reduction method tend to overestimate the efforts of intricate slopes compared with the evaluated method proposed in this simulation. This parallel comparison serves to validate the accuracy of the double strength reduction method proposed in the present study. Further, based on the proposed method, the relationship between slope stability and slope displacement is established. which provides a theoretical basis for the safety assessment of slope engineering. The rapid development of rock engineering, including the fields of mining, energy transportation, and so on, result in the geological environment becoming more complex and difficult to manage when employing these engineering methods. The increasing depths of open pit mining and the height of the slope engineering relative to dam and roads cause the safety and security of slope structures to be compromised, resulting in slope stability becoming critical to the long-term safe operation of rock engineering. Landslides predominantly arise from the following two aspects: the external force, which could break the initial stress equilibrium of the geological body and may cause slope collapse or sliding. The other is the change in the geological properties that cause the shear strength of geological body to decrease. A slip disaster can have substantial consequences such as the blockage of roadways, the interruption of traffic flow, and the structural collapse. However, there is no uniform standard for judging slope stability. Due to the complex mechanisms of slope destabilization, therefore, understanding the causative factors of slope landslides and developing scientific stability evaluation criteria are essential for the safety of slopes. The most common methods for assessing slope stability are the limit equilibrium method and the strength reduction method. The limit equilibrium approach necessitates the consideration of the sliding body as a rigid solid and the assumption or prior knowledge of the location and the shapes of the sliding surface. Determining the precise position of the sliding surface of a landslide is challenging in practical application. Unlike the limit equilibrium approach, the strength reduction method can be readily operationalized by automatically identifying the geological engineering, employ analytical and empirical methods to evaluate the safety factor of soil or rock material depending on design requirement and engineering characteristics. Engineers frequently use the factor of safety as a measure to evaluate slope stability and is widely recognized as a reliable safety indicator because of its practicality for engineering applications. The proportional reduction approach were employed by researcher assesses the stability of a concrete dam, and the other researchers used a new field element method scheme to develop the limit equilibrium equation for different proportional reduction parameters. They also explain the rotational behind using different proportional reductions for the cohesion and friction angle. A qualitative examination of the effects of cohesion and friction angle and slope stability was conducted by researchers and using the finite difference approach. The analysis in the reference study indicates that the present understanding of the influence of cohesion and friction angle on slope stability is primarily qualitative, lacking a quantitative approach to establish this relationship. The strength reduction method is distinguished by its clear physical significance of parameters and its ease of implementation through computer programming. Therefore, the development of its numerical computation method is highly important for the stability analysis of complex slopes. The finite element method has become a primary approach for quantitative assessing slope stability due to its modeling convenience and computational efficiency. With advancement in computer technology, FEM has gone significant attention and is now commonly used to evaluate the factor of safety as an alternative methodology, and the FEM strength reduction technique offers several notable advantages over traditional limit equilibrium and limit analysis methods. This simulation aims to explore the theory and application of the finite element multiple double stage reduction coefficient method in a slope stability analysis, building upon the established development of the finite element strange reduction method. This simulation presents a novel approach for analyzing slope stability by introducing a strange coefficient reduction method based on the shear strange parameter. The reliability of the proposed method was verified by the case study. This method contributes to the development of a comprehensive set of techniques for evaluating slope stability. This simulation employs a methodology to examine the stability of both homogeneous soil slopes and complex soil slopes, and subsequently derives the following conclusions. The computational process for this method is derived, and coefficients of safety for homogeneous soil slopes are determined using three methods: the conventional general strip partition (MP method), the finite element strange double reduction coefficient method, and the final is the general strip partition double reduction coefficient method. And now we go to the computer simulation. The strange reduction technique is a tool to find the factor of safety (FOS) in geotechnical problems, particularly in slope stability analysis. To determine the factor of safety of a slope, the strange property of the Moore-Coulomb model are gradually reduced until failure occurs. A comparison between associative and non-associative plastic flow is made. The strength reduction method, in the combination with the finite element analysis, is a tool to find the factor of safety in geomechanics, particularly for the stability of a slope and embankments. In the strength reduction method, the characteristics material properties are gradually reduced until the failure occurs. Also, the definition of an FOS depends on the context. In geotechnical problems, it is defined with respect to the strange parameters of the soil, and the strange reduction method is applicable to linear failure criteria like the Moore-Colombo criteria. When the Moore-Colombo criterion is used with the strange reduction method, the cohesion, the angle of internal friction, and the dilatation angle are simultaneously reduced until mechanical equilibrium is lost. Decreasing the material parameters results in a reduction of the shear strength of the soil, which eventually becomes unstable. This phenomenon produces a collapse of the slope for a certain combination of loads, material parameters, and boundary conditions. The ratio between the initial cohesion and the cohesion at failure gives the FOS. More details have been given in this simulation. The geometry, boundary condition, loading conditions, and material parameters in this example have been given here in this configuration, in this capsule simulation. And here we can see the components that we have used a geometry of a two-dimensional dam, and the physical model that we have used is the solid mechanic to assign the force, gravity, and the specific material is a soil material with a specific Young module and Poisson ratio, and the soil material specification. We have initial values, and also we make a part of this geometry as a free, and we make some part as a fixed. The bottom is fixed and it's not collapsing, but the free part can be collapsed. As a result, we can see the displacement versus FOS plot, and also the deformation in a three-dimensional section. And you can see this is a dam, and the bottom side is fixed, constrained, and you can see the slope in this section of the dam. Thank you so much for watching my tutorial video until the end, and also you can download this computer simulation from github.com/masterscript.